In this video, we introduce the topic of contour integrals on the complex plane. We will work out some examples to illustrate how to calculate contour integrals. But first, a few definitions are in order. Let C be a curve on a complex plane given by the parametric equation z equals f of t that is defined and continuous on the closed interval from alpha to beta, where alpha and beta are real numbers. Suppose that f prime exists and is continuous. We also assume that f prime is not equal to 0 except possibly at alpha or beta. Then we say that C is a regular curve. Let z be equal to x plus iy, where x and y are real numbers. Let the real part of f of t be f sub 1 of t, and let the imaginary part of f of t be f sub 2 of t. If z is a point on C, then x and y are given parametrically by this vector equation. Now we take the same f in the definition, but we suppose that this time there exists a partition t sub 0 which is equal to alpha, which is less than t sub 1, which is less than t sub 2, etc., 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 all the way up to t sub n, which equals beta, such that the restriction f sub k of f on the subinterval from t sub k minus 1 to t sub k is a regular curve on the subinterval for k equals 1 to n. Then we say that f is a piecewise regular curve and C is a contour on the complex plane. As an exercise, we describe the contour C that is given by the equation z equals the square of t plus I, where t is between 0 and 1. T plus I quantity squared is t squared minus 1 plus 2it, so that x equals t squared minus 1 and y equals 2t. So y over 2 equals t, and plugging this into the x parameterization, x equals y over 2 quantity squared minus 1, or y squared over 4 minus 1, which is the equation of a parabola. Therefore, the points on C are points on the parabola x equals y squared over 4 minus 1. To determine precisely which points on the parabola comprise C, we observe that x equals t squared minus 1 and y equals 2t simultaneously increase on the interval from t equals 0 to t equals 1. When t equals 0, x equals minus 1 and y equals 0. And when t equals 1, x equals 0 and y equals 2. Since x and y both increase as t goes from 0 to 1, C is the arc on the parabola that starts at the point minus 1, 0 and ends at the point 0, 2. We again take the contour C given by the equation z equals f of t, where t is between alpha and beta. We assume that f prime is defined and bounded on the closed interval from alpha to beta, and continuous except for a finite number of values on the interval. Let g be a continuous complex valued function on the complex plane. We denote the contour integral of g along C this way. The contour integral of g along C is given by the integral with respect to t from alpha to beta of g of f of t times f prime of t. As an example, we set up and find the value of the contour integral of z squared along the contour C that is given by the triangle with sides c sub 1, c sub 2, and c sub 3, and with a given orientation or direction as indicated by the arrows. C sub 1 is the line segment from 0 to 1. C sub 2 is the line segment from 1 to 1 plus I. And C sub 3 is the line segment from 1 plus I back to 0. We say that C is oriented counterclockwise. To be more precise, we also say that C is oriented positively. To understand what positive orientation means, imagine a lizard or a gecko following the orientation of C as indicated by the arrows. If the gecko keeps the interior of C to its left as it follows the orientation of C, then we say that contour C is oriented positively. The contour integral of z squared along C equals the contour integral along C sub 1 plus the contour integral along C sub 2 plus the contour integral along C sub 3. We first parameterize C sub 1, C sub 2, and C sub 3. For c sub 1, since x goes from 0 to 1 while y stays constant at 0, we set x equal to t and y equal to 0, with 0 less than or equal to t less than or equal to 1. So z equals t and z prime equals 1, which is definitely non-zero. For c sub 2, x is fixed at 1 and y increases from 0 to 1. So we set x equal to 1 and y equal to t with t between 0 and 1 so that z equals 1 plus I t. Z prime equals I, which again is non-zero. For c sub 3, both x and y start at 1 and end at 0, so we set both x and y equal to 1 minus t, with 0 less than or equal to t less than or equal to 1. So z equals 1 minus t plus I times the quantity 1 minus t, or the product of 1 plus I and 1 minus t. We could have also arrived at this parameterization by using a standard parameterization of a line segment. Z equals the initial or starting point 1 plus I plus t times the difference between the terminal or final point, which is 0, and the initial point, which is 1 plus I. This factors out into the product of 1 plus I and 1 minus t. Z prime equals minus 1 minus I, which again is non-zero. So the contour integral of z squared along c sub 1 equals the integral from t equals 0 to t equals 1 of z squared, or t squared, since z equals t times z prime, or 1. This equals 1/3. The contour integral of z squared along c sub 2 equals the integral from t equals 0 to t equals 1 of the square of 1 plus it, since z equals 1 plus it on c sub 2, times z prime, or I, and this equals minus 1 plus 2i over 3. For the contour integral of z squared along c sub 3, we square the product of 1 plus I and 1 minus t, multiply the result by z prime, or minus 1 minus I, and integrate from t equals 0 to t equals 1. The value of the integral is 2/3 minus 2i over 3. We add these all up and find that the contour integral of z squared around c equals 0. For the next example, we find the value of the contour integral of z minus z sub 0 to the nth power, where n is an integer and c is the circle centered at z sub 0 with radius r and oriented positively. Let z be a point on the circle. If the real part of z sub 0 is x sub 0 and its imaginary part is y sub 0, then z minus z sub 0 equals x minus x sub 0 plus I times the quantity y minus y sub 0. X minus x sub 0 is equal to r times cosine t, where t is an argument of z minus z sub 0. Y minus y sub 0 equals r times sine t. So z minus z sub 0 equals r times cosine t plus I times r times sine t, or r times e raised to the power I times t. Therefore, z equals z sub 0 plus r times e raised to the power I times t. We set t to be between 0 and 2 pi. Z prime equals I times r times e raised to the power I times t, which is never 0. And so inside the integral, we have the nth power of r times e raised to the power I times t, or r to the nth power, times e raised to the power I times n times t. dz is I times r times e raised to the power I times t dt. And so in the integrand, we have the constants I and r raised to the n plus 1th power. The exponentials combine to become e raised to the power I times n plus 1 times t. An antiderivative would be I times r to the n plus 1th power times e raised to the power I times n plus 1 times t over I times n plus 1. N plus 1 in the denominator is 0 when n equals minus 1. So we first deal with the case when n is not equal to -1. When t is either 0 or 2 pi, e raised to the power I times n plus 1 times t equals 1, so that the values of the antiderivative at 0 and 2 pi cancel each other out, and the contour integral equals 0 when n is not equal to -1. When n equals -1, r raised to the n plus 1 power in the integrand is r to the 0th power, which equals 1. And the exponential becomes e to the 0th power, which is also 1. So that the only thing left in the integrand is the constant I. So when n equals -1, the contour integral equals I times the length of the interval of integration, which is 2 pi, so we have 2 pi times I for the value of the contour integral. Therefore, the contour integral of z minus z sub 0 to the nth power along C equals 0 when n is not equal to -1, and equals 2 pi times I when n equals -1.